2,000 years, we humans, the same humans who have built rockets which have sent us to space, the same humans who have utilized equations which have let us understand how waves behave, have yet to produce a machine which can detect P waves from an earthquake.
Alright, so hey guys, and so in this video for the Breakthrough Junior Challenge, I'm going to talk about how we can build an early earthquake detection algorithm to warn people by using phones, Bayesian probability, electromagnetic waves, and a few other methods. So let's get started. So my name is Rifat, and today we're going to discuss four things. First, the earthquake's attributes and characteristics. Second, the first method to detecting an earthquake, the social media keyword algorithm. Third, detecting an earthquake using electromagnetic waves. And fourth, using a phone accelerometer to detect an earthquake. So let's begin with the earthquake attributes and characteristics. So we have two types of body waves. First we have the P wave and then the S wave. So the P wave can travel through all states of matter, including solid.
Why you gotta take so long?
Alright, fine, speed it up, folks. So it can travel through solids, for example, the Earth's crust. You still talk like Bigfoot. So, we would say that this is the Earth's crust, and that this is the Earth's mantle. So, a P wave can travel through solids, such as the Earth's crust. It can also travel through liquids, such as tsunamis. So, an earthquake can also travel through such types of matter, for example, tsunami.
You're still very slow.
It is warned that when a heavy earthquake occurs, a tsunami may also travel forward with that earthquake. So P waves can travel through most types of states of matter. Now, a P wave is also slower than an S wave. That's why a P wave it's faster than an S wave, so it actually comes first to the destination. So this is the epicenter of the earthquake. The P wave would go faster at about 2.8 miles per hour. While the S wave would travel at about only 2,000 miles per hour. So, if we looked at a seismogram, this is how it would appear. We would have the earthquake epicenter, and then shaking from the P wave. So we know that right over here is the start of the P wave, and once the P wave ceases, we have the S waves, which are a lot more stronger. So right over here we can see is the start of the S wave. High contrast color. So this would be the start of the S wave. Now, an S wave can only travel to solids. So, for example, if a tsunami occurs because of an earthquake, there will never be like a double warning like an earthquake. There will only be the P wave, no S wave. So an S wave can only travel through solid. Now we're going to discuss about how we can detect the epicenter of the earthquake. Alright, so now that we know the attributes and characteristics of an earthquake, let's move on to how to detect an earthquake using social media. So, for example, let's say we have something like Twitter. So, to build an algorithm that detects whatever tweets are warning an earthquake, first we have to detect the keyword. So, for example, quake, UTC for timing, minutes for also timing, ago, if it's compensated with minutes, location, if the location matches any of the locations in a specific array. So for example, I'll have an array that has all the locations, all the countries on Earth, and as well as the Richter scale of the earthquake. So for example, M followed by a real number with a decimal. Second, to build our algorithm, we have to get all the messages that contain those specific keywords and store them in an array. So if we make an array called all tweets, that would store all the tweets that have those specific keywords. Third of all, to get even more specific, we want to use the floor function to round the number of minutes since the tweet was posted since the earthquake. So for example, if the tweet has minutes, so for example, in this tweet it says Justin 50 earthquake 557 GMT MT. Did we just have an earthquake? So it'll measure that time minus the time the tweet was posted, and it'll find the number of minutes since the tweet was posted after the earthquake. So after that, we're gonna list the top 3 messages posted since the shortest time after the quake, and we're going to copy the warning from those tweets across all governmental phones within the specific radius of the earthquake speed wave. And so that's how we'll use a social media for like Twitter or Facebook or something as such to warn users of an earthquake. So now let's move on to how we can utilize electromagnetic waves to detect earthquakes. So let's say, we know that an average earthquake, or for example a sample earthquake, emits from 0 to 20 hertz of electromagnetic waves from the epicenter. So what can we do to detect those electromagnetic waves? Well, we know that an antenna can detect those EM waves, so we can just wrap an antenna around the base of the phone and stick a part of that antenna out so that the EM waves from the earthquake can be detected. And so that's how we utilize EM waves to detect an earthquake. Now last of all, we can utilize a phone's accelerometer to detect an earthquake. So how can we do that? Well, if you take a look at the iOS developer library, we'll see something called a piece of code called the accelerometer graph. That accelerometer graph graphs out the motion that the phone is shaking, or its roll and its axis. So its pitch, its yaw, its roll, it's basically its angle of movement. So we can plot any significant shaking within the graph of the accelerometer due to the earthquake. So, for example, the earthquake, even if the person who's using the phone doesn't realize it, the phone accelerometer will graph the slight shaking. That significant sudden shake will cause an alarm, a chain reaction basically, in seconds after the first person. And so that is how we utilize a phone accelerometer to warn people about an earthquake, as well as detect